In this video we're going to look at the Opamp frequency response and also look at dominant pole compensation. So an Opamp, as we'd mentioned previously, can be split into three main sections. There's going to be an input stage, which is a differential amplifier, a gain stage, which is another amplifier that provides most of the gain, and also an output stage. Now the frequency and phase response for each of these individual stages is drawn here. Okay, so the gain stage here is in yellow, so you can see the gain stage. It's obviously getting the maximum gain up at 60 dBs, and it's also got the widest frequency response. The differential stage here is going to have some gain associated with it, and also we're going to have an output stage there with a little bit of gain associated with that as well. So you can see here that each of these stages is going to introduce a 20 dB per decade decrease as the frequency increases, and the phase response is drawn here as well. So we're going to have a low pass phase response here, and the yellow one is the gain, the pink is the differential, the blue is the output stage. So these are the magnitude and phase response for a typical operational amplifier which requires compensation. So we've seen in the previous videos that in order to ensure stability, we have to make sure that if the phase is minus 180 degrees at some value, say omega 1, then we see that we end up with a positive feedback. So we need to ensure that that doesn't occur, and there's several different ways of doing that to prevent that form of instability. Now the prevention of that instability is called compensation. So the common ways are introducing one of the common ways is introducing a dominant pole, and there's also another method called pole splitting. So we're not going to go over pole splitting at the moment. I might add it in at the end as an extra bonus video. So we're going to look at the simple dominant pole compensation. So let's have a wee look at that. So if we were to add up the three different stages of the Opamp which we've shown in the previous page, we would get the magnitude and phase response that we see here in blue. So you can see it's going to have a 20 dB per decade decrease here, and then the second stage will give it a 40 dB per decade decrease, and the final stage will be a 60 dB per decade decrease. Okay, and you can see the phase response here as well. Now we can see from this here that this Opamp isn't going to be stable, because when the phase is at minus 180 degrees, so we're going to have positive feedback. So we'll have positive feedback at this frequency up here, just over 100k. So at that frequency you can see there's a gain of 50 dB. So it means that when we have positive feedback at that frequency, the signal is going to be amplified, continually amplified around the system. So that's going to be an unstable Opamp, and you can also see that the phase margin here is going to be minus 65 degrees. So we can see that here the 0 dB gain here occurs away down at this minus over 200 and say 240 odd degrees. So it's 65 degrees, so it's minus 245 degrees, so it's 65 degrees worse than the 180. Okay, so that there is not going to be a stable Opamp. So we need to stabilize this Opamp, and we need to get an acceptable gain margin on phase margin. Okay, so the Opamp, we say, is going to need compensation. So we're going to consider the simplest form of compensation called dominant pole compensation. So this really makes the response look like a simple first order low pass filter by introducing a pole at a low frequency. So we'll introduce, in order to get that pole, we're going to introduce an RC filter, which is just really a low pass filter on the output of the op-amp. And we're going to have to work out what the cut-off frequency of this filter has to be. Okay, so we're going to have to decide which phase margin we're going to want. So a typical phase margin, we've mentioned before in one of the other videos, is going to be 60 degrees. So it would mean that we would need 180 minus a minus 60, which would be a 120 degrees at the output of the fourth order system. So it's fourth order because we've got the three orders in the op-amp, which are given by the gain, the differential and the output phase, and also another order given by the RC filter. Okay, so we have to include also the fact that the RC filter, well, the capacitance in RC filter is going to add another 90 degrees of phase shift. Okay, so it means then that no, we don't actually want to have minus 120 degrees, we need to take another 90 degrees extra as well. So it means we're going to need a value of minus 30 degrees at the output of the fourth order system. So the frequency when the phase is minus 30 degrees is going to be approximately equal to the 5000 radians per second, and you can see that there from the previous drawing. I'll bring it up here, so you can see that we have at our minus 30 degrees, which is just up about here, minus 30 degrees. Get that fixed. Okay, so minus 30 degrees here. Okay, if we were to come across here and we come up, we see that that occurs at a frequency which is halfway between the maybe the 1 and the 10. So it's round about, well, let's say it's round about 5,000 and it's in radians per second. Okay. So the frequency at which the phase is minus 30 degrees C, 30 degrees, is 5000 radians per second. So the gain of a compensated op-amp must be 0 dBs to give the 60 degrees phase margin. It's got to be, obviously, it's got to be 0 dBs at 5000 radians per second. Okay, so let's look at the response of the RC filter. So what we're going to have here then is the value of our gain, our phase margin, is going to be 60 degrees. So for 180 to 60 degrees is 120. So that's going to give us a gain of 0 dBs at that point there, which is our 5000 radians per second. Okay, so it means that we know that at 0 dBs, it's got to go from 0 dBs up to 90 dBs. So it's got to go 4.5 lots of 20. Okay, so it's going to go 20, 40, 60, 80, and then a half of the 20. So it's 4.5 times the 20. So it means the cut-off frequency is going to be 4.5 decades less than the 5000 radians per second. So we can say that it's going to be 5000 upon 10 times 10 to the power of 4.5, which is approximately equal to 0.158 radians per second. So we've seen from previous videos that we can work out the cut-off frequency of a low pass filter there. It's going to be given by 1 upon 2 pi RC. So we know the value of the 2 pi f, which is our value of our frequency in radians, which is radians per second, which is going to be 0.158. So 0.158 is going to equal 1 upon RC. So we can say RC is going to equal 1 upon 0.158. So if we let R equal say 10,000, then that would ensure that C would be a value of 15.8 microfarads. So this would introduce a dominant pole at a correct position in order to ensure that we've got a 60 degrees of phase margin. Okay, so that's a little example of how to compensate an op-amp. Now, the transfer function approximation for this, we can see that as a compensated op-amp, it looks like a first order low pass filter up to a unity gain, that is a gain of 1. Then the transfer function can be approximated by the low pass filter function, which is h of s is equals 1 upon 1 plus src. So then we can say h of s is going to equal 1 upon 1 plus the value of s, and we can replace our rc with our value omega c, okay, because we know that omega c equals 1 upon rc. Okay, that just comes from the equation we've seen above, where fc equals 1 upon 2 pi rc. Okay, so the f is just the 2 pi is incorporated into this omega c here. Okay, so that means then that if we were to choose a value for the gain to be the value of the frequency to be the frequency that gives us a unity gain, okay, so the frequency at which the gain is equal to 1, then we could say that the open loop gain at the frequency that gives us a unity gain is going to equal, well, it's going to equal the omega, which we've now chosen for s, which is going to be the unity gain value for the value of omega. And also to note here is that the value of 1 there, well, that's a constant in this term, and remember that we're actually dealing with an active circuit, so there's actually a gain associated with this. So that constant in an active circuit with an open loop gain is actually going to be a different value. Okay, in this instance here, it'll be the open loop DC gain of the op-amp. So we can say then that the open loop DC gain of the op-amp divided by 1 plus j omega of the unity gain upon omega c is going to equal the value of 1, because it's the unity gain. But we know that the omega is going to be very high for that unity gain, so it means that this term here is going to dominate, so we can really kind of forget about that value of 1. So we're also able to say then that as this value omega unity gain dominates as well, it'll dominate this value for omega c. So it means that we can take this up to one side here. So we're going to have the omega unity gain is just going to equal the open loop DC gain times, and we've taken the omega c up to the other side here, times the omega c. Now we can see then for a 741 op-amp that the FC is approximately equal to 10 Hz. Okay, so that the cut-off frequency is equal to 10 Hz, and the open loop gain is equal to 10 to the 5. So if we multiply 10 to the 5 times 10, we'll get 10 to the 6, which is approximately 1 megahertz, and 1 megahertz is approximately the unity gain of the 741 op-amp, meaning the gain drops to a value of 1 megahertz. Okay, so that just shows that the little part of this proof does actually add up in reality. Okay, so that's all there is for this video, and I'll get you on the next video in which we're going to take a look at the frequency response of an op-amp with negative feedback. Okay, so thank you for listening and goodbye.